Song?
So before we get started, I just wanted to say we do appear to have been experiencing some microphone difficulties. So we may have lost a little of the audio for Sakura, and people told me that some of the audio for Hong from today was lost. So we swapped out some batteries, so it should be good going forward. Let us know if there are any further problems, but those two, we may have lost some already, but hopefully it'll be okay. So let's go back to our discussions of CFTs and generalized symmetries.
All right. Welcome back, everyone. So as I said yesterday, I didn't finish my lesson plan, but I did upload what I planned to cover as a handwritten note to the Google Dropbox, Google Drive, not Google Dropbox. And I hope you had a chance to look at it, and hopefully it was a review for most of you. But even if you have not seen it before, I will start today by emphasizing some of the key points that we'll make use of in the following discussion. So one thing that I really wanted to get across yesterday was the notion of this enhanced conformal symmetry in 2 dimensions, namely the Virasoro symmetry, which is an extension of the global conformal symmetry in 3 dimensions, generated by this holomorphic generators Ln and anti-holomorphic generators Ln bar. And the special cases when n is equal to plus minus 1 and 0, they generate the global conformal symmetry, SO 1, 3. Okay? But this is going to be an infinite extension that generates the so-called Virasoro algebra. And we derived the corresponding commutation relation for the Virasoro algebra towards the end of the last lecture. And whenever you have a symmetry, okay, in quantum field theory, the first thing you want to study is constraints from the symmetry on the spectrum of states. And in this case, because the operator state correspondence is equivalent to study constraints on the spectrum of operators. So what we have as a consequence is that the CFT operators, okay, or equivalently the states in the Hilbert space on S1 by the operator state correspondence, they will be organized into representations of the Virasoro symmetry. And for simplicity, I'll focus on the case when the holomorphic and the anti-holomorphic Virasoro symmetry are characterized by the same center charge, namely C equal to C bar. Okay? That corresponds to the case when there's no gravitational anomaly. There are interesting physics in the cases when they are not the same, but for simplicity, we'll focus on this case. Now, I left something blank here because we're not interested in just arbitrary 2-dimensional CFT. We're interested in CFT that has satisfied the set of criterion I mentioned, unitarity, locality. So in particular, and compactness, namely you have a discrete spectrum when you study the theory on the compact space. So these are not going to be the arbitrary representation that describe the CFT operators. There will be unitary representations. Okay, this is very important. And this unitarity strongly constrains on what kind of CFT operators are admissible in CFT. And to study the constraints coming from unitarity, it's crucial to understand what is the hermiticity property of these generators. So this could be something that's slightly confusing when you first look at it. But you should remember that hermiticity is inherited from the Laurentine cylinder picture that we described last class. And the Hermitian conjugate does not map the L to L bar. Okay, and that's going to be a common confusion when you first look at CFT. And the Hermitian conjugate, instead, as you can derive from the general discussion we had last time, in this case, particular for the stress tensor, okay, for which this Ln are the holomorphic and anti-holomorphic modes, the Hermitian conjugate is defined as follows. Okay. All right. So how does this unitarity constraint look like? Okay. The unitarity constraint take the following form. To start, first of all, we can diagonalize every state in the Hilbert space according to its dimension, according to its eigenvalue with respect to L0 and L0 bar, which are Hermitian, okay, thanks to this condition. Both of them are Hermitian, and they are mutually commuting. Okay, so I can diagonalize my Hilbert space by grading the states by these quantum numbers. And delta, the scaling dimension, which is universal to conformal field theory in all dimensions, is characterized by the sum of the eigenvalues with respect to L0 and L0 bar. And the spin, okay, the analog of the spin higher dimension, now we focus on the 2-dimension, will be related to the, so if I write in terms of eigenvalues, just h plus h bar, and the spin is the difference between h and h bar, the absolute value. Okay, it tells you about how the operator transform and corresponding to the state under SO2 rotation that fix the location of the operator insertion. Now, the unitarity will constrain what these values of h could be. Okay, in particular, unitarity will tell you that h and h bar has to be non-negative, okay, and also c is non-negative. And the interesting case, c will be bigger than 0, otherwise the theory will be topological. And the systematic way to analyze this is to realize that you can organize, using the T structure, you can organize the states in Hilbert space into towers known as conformal multiplets. So I'll label them by MCH, okay, with H bar as well. And there's a distinguished state, a distinguished operator in each multiplet. So this will be the representation. Okay, this will, by definition, this will be the representation of the Virasoro symmetry. And because the Virasoro symmetry factorizes, for simplicity, let me just focus on the representation with respect to the left, or the holomorphic Virasoro algebra. Okay. In each such representation, there's a distinguished guy. That's the primary operator. And they label its conformal dimension as follows. And this corresponds to some state in the Hilbert space, okay, labeled by the corresponding quantum numbers with respect to L0 and L0 bar. The fact it being a primary means that it's annihilated by the Virasoro generators, where n is bigger than 0. Okay, and all the other. So okay, just to be very precise, I think this is really the tensor product of these two representations. I'm writing on the right-hand side because I'm keeping track of both NH and H bar. Okay, and the rest of the guys in the multiplets are descendants, and they're coming from the Virasoro generators with negative subscript acting on the primary states. So in terms of operators, can be thought of as acting with commutator on the operator insertion, okay, where n is positive, and they correspond to state coming from L minus, okay, or L minus L bar minus, similar for the anti-holomorphic generators. Okay. And you can repeatedly act on these local operators and corresponding states with this confusing. It may be confusing with these racing operators. They're racing in the sense that they increase the conformal dimension, and the way you can see that these generators with negative subscript increase the conformal dimension is by looking at the Virasoro algebra. Okay, they're just like the raising operators that you encounter in quantum mechanics. Okay, and what is the constraint on unitarity? Okay, so you can postulate that you have a multiplet of this type. Okay, and by construction, this multiplet is closes under action of the Virasoro symmetry. Okay, and the constraint coming from unitarity says that every state that in this multiplet must have a positive definite norm. Okay, or more precisely, is that you calculate the matrix that's coming, the grand matrix that's coming from the various state in this multiplet. So this is the grand matrix. Okay, for each state in this multiplet, and you insist on this matrix being positive definite. Okay, and by doing so, you fully exhaust the constraints coming from unitarity on these representations. Okay, so I'll not do that exercise here, but I'll just summarize what answers you will find. Okay, there will be some constraint on the conformal dimension or scaling dimension of the operators that may depend on the center charge. Okay, the constraint is rather simple if the center charge. There's a very simple constraint. First of all, it's coming from is what I already wrote over there. It's generically true for c bigger than 0. That is simply the condition that h and h bar has to be non-negative, and moreover, when h and h bar is equal to 0, okay, the corresponding state is invariant under the full global conformal symmetry. Okay, so that is a special case. In terms of this algebra generators, it's a special case where L minus 1 acting on this state is also 0. Okay, and this is also the reason why I label the state in this way, because this is precisely what happens to the vacuum of the CFT. Okay, with the property that I mentioned, necessarily means that it will be invariant under the global conformal symmetry. The constraint from unitarity is more interesting, okay, when center charge is small. So I'll not be exhaustive in the constraints, and you can find them. You can find some of the discussion in the notes I sent and in the references that I put in the Google Drive. Yeah, question, yes. Oh. Yeah, so in this, so I should have also made that clarification. In this set of lectures, I will be studying not just unitary compact local CFT, but also CFTs with unique vacuum. Okay. In general, you can have a CFT with degenerate vacuum. For example, you can get by stacking a CFT with a GQFT. Okay. Thanks for the question. All right. So back to the consequence of unitarity. The constraint is particularly strong in the case when C is smaller than 1. In which case you find that there's discrete possibilities for what are the values of C and H that are compatible with unitarity. Okay. So for those of you who have seen this before, these are the values that correspond to the scaling dimensions that are admissible, that are realized in the so-called minimum models. Okay. There are a sequence of theories where the center charge are labeled by integer m, start from 3, 4, and 5, and so on. Okay. And the special case when m is equal to 3 is the center charge of the Ising CFT, namely c equal to 1/2. And this corresponds to tricritical Ising and so on. So not only the center charge is restricted to take discrete values the moment you focus on the case where c is smaller than 1 and just studying the unitarity constraints, you also find that the scaling dimensions, the possible conformal multiplets in order to obey unitarity, is constrained to take discrete values that depend on C or equivalently depending on M. And this set of possible values for h compatible with unitarity can be parameterized by two integers, r and s. That is a function that depends on m. Detail is not important. Here, I just want to emphasize it's a finite set where r is restricted to between m minus 1 and 1, and s between r and 1. Okay, so it's like in the triangular region. And again, in the special case, when m is equal to 3, okay, that correspond to that has the center chart that corresponds to the Ising CFT, the possible h has 3 possibilities, okay? And they're either h equal to 0, h equal to 1/2, and h equal to 1/16. Okay? So it's very restrictive just from studying, just from using conformal symmetry and unitarity. Okay? Looking at the spectrum, you already find that for c equal to 1/2, you only have very restricted possibilities for what operators are admissible in such a conformal field theory. Okay? And later on, we'll see that these are realized, in particular, in the Ising CFT. Okay? So here, we're being agnostic about the potential degeneracies of these scaling dimensions appearing in the actual CFT. But later, we'll see that these scaling dimensions will appear with unit degeneracy. Okay? Each of them will appear once in the actual CFT. And that, to fix that, require additional constraints coming from a locality, which we have not used so far. Okay? All right. Okay, so instead of jumping into the general axioms onto these CFTs coming from a locality, which by which I mean the consistency of cutting and gluing a general observable in the 2D CFT, let's focus on a particular constraint from locality, which is already very powerful. That comes from studying conformal field theory on the torus. And the corresponding constraint, that's, as we'll see, is a general consequence of locality, will be modular invariance. Okay? So the main player here is the torus splitting function, which you have already seen, not in the relativistic quantum field theory, but for the lattice model in Nati's lecture. So the torus splitting function is a function of the dimensionless geometric modulus of the underlying spacetime manifold, because we have a CFT. This manifold you can represent as a fundamental domain in some lattice, okay, on the complex plane, and they'll use the coordinates w, and for convenience, I'll scale by a factor of 2 pi. Okay, so w is this parameterized this complex plane. And I can think about torus as this fundamental domain on the lattice defined by this identification. Okay, so that this point corresponds to 0. This corresponds to 1, and this is tau. Okay, in particular, this vertical height of the torus is tau 2. Okay, and you can, if you want, you can think about this as time direction. And this tau 2 is the direction of the cylinder, which you glue together the end and the top and the bottom to construct this torus. And this tau 1, okay, is the shift that you implement when you do that gluing. Okay, so with that picture in mind, you can interpret, think about this direction as time, and this direction as generated by a translation in the spatial direction on the cylinder. You can think about this torus splitting function as a trace over the Hilbert space on S1 in this direction in this picture. Okay, where you have the evolution in the time direction coming from the Hamiltonian on the cylinder. Okay, by the time step tau 2, and then in addition, this shift in the spatial direction by amount tau 1. Using the translation operator P, okay, again on the cylinder. And using the relation between operators under Wall transformation, okay, in particular the stress tensor, you can find that the Hamiltonian On the cylinder, it's realized in terms of the Virasoro generators on the plane in the following way. It's equal to L0 plus L0 bar minus C over 24. And recall, this is precisely the dilatation operator that we had before. And so it's not surprising, as we said before, the dilatation operator generates radial evolution on the plane. And under Wang transformation, that becomes the time evolution on the cylinder. Okay? And this shift is coming from the famous Schwarzian. That is one manifestation of the conformal anomaly for two-dimensional CFT. Okay? When you go between the plane to the cylinder, which involves this Wang transformation. Okay?
Is there a pi in the first exponent?
Pi?
I?
No, there's no I. We're looking at the Euclidean. Okay? Torus is the Euclidean function. Okay? And this on the other hand, this P is something that you have already seen in Nadi's talk, which is the momentum generators that generates the translation along the, in this case, the circle direction. And in terms of the Virasoro generator, is simply the difference between these two. And this is also we have been referring to as spin. So while used interchangeably this language spin, quantum numbers, eigenvalues of this, and the shift momentum. Okay. So in Nadi's talk, it was referred to as the shift momentum because that's the natural language on the torus. Okay. All right. So using this relation, okay, this equality can be written in a compact way by introducing this. Okay, we have enough space. Introducing this convenient Q parameter, which is just a way to parameterize this modulus tau of this torus. And again, we're focusing on, for simplicity, in the case that there's no gravitational anomaly, so the left and right center charge are taken to be the same. And Q is just e to the 2 pi I tau, and Q bar is this complex conjugate. Okay, so emphasize to be maximally, well, yeah. So if you want to really kind of disentangle the different notion between complex conjugate and, okay. Anyways, I will not get into there. I think notation I'm using is self-consistent, but the bar has different meanings. That's what I'm saying. Yeah. Question? Yeah.
So should it be like minus 0 to 1 or it's still in the
Sorry. Yeah. This is the total. Yeah. Thank you for pointing that out. Yes. Okay. Good. All right. Okay, this. All right. So that is this very important object that we'll study and refine by including symmetry twist later. But before getting there, there are already some very interesting features of this torus Platin function that would lead to these non-trivial constraints onto these CFTs. Okay. So let's kind of maybe stare at this expression and highlight some of the important features. So one important feature is that it's positive. Okay, so why is that? It's because we have a trace over a Hilbert space. Okay, we're tracing over states in Hilbert space where so we're just counting states. Okay, and each state contribute with some degeneracy, and it's weighted by this quantity. Okay, so all the coefficients that appear in the expansion in terms of Q and Q bar come with positive coefficients. And moreover, because we're counting states, it's also in addition to being positive, it's also integral. Okay, so in the coefficient in this Q bar expansion is positive and integral. Okay, but we can do better than that. Okay, so this will be true for general quantum field theory. This statement is true for general quantum field theory. But in the case of conformal symmetry, okay, in the presence of conformal symmetry, the states in the Hilbert space, as we explained over here, are further organized into representations of conformal symmetry. Okay, so the positivity gets enhanced by the fact that you can write this torus Platin function, okay, not just as a positive integral sum of Q and Q bar expansion, but instead as a sum of basic building blocks that keeps track of the symmetry property. Okay, keep track of the representation content. And those are known as Virasoro characters, okay, which I'll call chi. And these characters, and there will be some coefficient that are non-negative integers. And you sum over the possible values of h and h bar that are realized in the CFT spectrum. And these Virasoro characters is nothing but the trace restricted to a given conformal multiplet. Okay. So this is the first fact that's very important about this object. The second fact is that this, as a function of tau, it's not an arbitrary function of tau. It's very important, not in addition to being positive integral, it has a very important property that is modular invariance. It's coming from the fact that thinking about the torus, okay, as C2 modeled by these discrete identifications, okay, essentially you are quotienting C2 by a two lattice, okay. You are free to choose what is your choice of a fundamental domain. For example, here I made a choice to look like this, but I can choose a fundamental domain that look like something like this, okay. And that corresponds to apparent change in the value of tau by shifting by 1, okay? But they describe the same torus. And similarly, there's an S transformation that corresponds to rotating the torus. And so just in terms of equations, these are the corresponding transformations. Okay? So these transformations, T and S, they generate a PSL2Z group. Okay? They generally act on this complex structure moduli by a fractional linear combination, much like the Mobius transformation that we introduced to describe the global conformal transformation. But the difference now is that the coefficients that enter in the fractional linear transformations are integers. Okay? And because doing these transformations, we're not changing the actual torus, the corresponding Patin function does not change. Okay? And that leads to a powerful constraint on these quantities. Okay? So in particular, as a consequence of this equation, you have this constraint on this torus Patin function. Question? Yes?
When you write down the ended for your particular function, I mean, some summation over the characters.
Yes.
Do you mean that the spectrum is discrete because we're doing a summation?
That's right. So in general, I do not need to assume that. I can consider an integral with some density. But as I said in the first lecture, for simplicity, we're treating the case when the theory is local, unitary, compact with unique vacuum. Thanks for that question. And compact means that I have a discrete spectrum on the circle. Okay. So for example, very interesting theories like alluvial theories, and some of you brought up in the questions, will have some integral here instead. Okay. But for simplicity, we'll not discuss it in this sequence of lectures. All right. So now the point is that by combining these two features of the torus Patin function, okay, we can say a lot about the 2D CFT without studying more general observable, like 4-point function and so on. Okay. So, and it is very surprising, and it's a consequence of the powerful, kind of more powerful conformal symmetry in 2 dimensions than in other dimensions. All right. So how does this constraints from modular invariance look like? So I can use this this part of the board maybe just to. Okay, maybe I'll move to the end of the board. Okay. So let's say constraints from modular invariance. One of these constraints is rather straightforward. That is invariant under the T transformation. Okay. What does T transformation do? Well, T transformation shifts tau by 1. Okay. And you look at the form of the character. Okay. The transformation of character is completely determined by the corresponding conformal weight. Okay. Why is that? That is because everything in the conformal multiplet, everything in the same conformal multiplet are obtained by generators with integral conformal dimensions hitting a primary operator. Okay? Those integral generators will not feel this shift, okay? Because the 2 pi I in my definition of Q. So consequently, T invariance, what T invariance implies is that the phase you get from doing T transformation, okay, on each of the summit over here need to cancel. And that's the condition that the spin, or in other words, the momentum on the transverse on this compact circle on the cylinder has to be integer. Okay, it's the usual spin quantization. Okay, and again, so here a small disclaimer that we'll be focusing on not just local unitary compact CFT with unique vacuum, but also bosonic CFTs. I hope I don't need to add more adjectives. Okay. Everything here I said here can be generalized for fermionic case, but just to limit the scope, let's focus on this case. The constraint from the invariance under this so-called S duality transformation, modular S transformation, is more interesting. And using the fact that the characters, okay, the Virasoro characters, transform in this way. Okay. So in general, the Virasoro characters transform by a complicated matrix. Okay. Again, if we forget about the compact case, in general, this will be some integral. Okay. Using this matrix, this will constrain the coefficient that appear in the torus Spartan function, which we put into the ansatz over here. Okay, and the constraint looks like schematically saying that this matrix, this is called the modular S matrix. Okay. And these are, and this is known as modular invariant. It's known as modular invariant because subject to this S invariant condition, essentially says that this S matrix contract with N, contract with S again, has to give N back. Okay? I'm just writing down a schematic equation. We'll go to concrete example to see where we see how this equation look like and how the explicit solution can be identified in a very simple way. Okay, so let's look at a very specific example. Okay, as a consequence of to analyze this equation, the modular invariance equation. That's the first application. First application of the constraint from modular invariance onto the CFTs. And this concerns the study of this putative Ising CFT, which we promised is something that's relevant for describing the seq to 1/2 conformal system. Okay? And just from representation theory, we already know the conformal scaling dimensions are constrained to these 3 possible values for H and also for H bar. And C is 1/2. The characters, I will not explain how you calculate. There's various subtleties that are going to actually calculate these characters, okay? In this case where C is more than 1. I explained some of that in the notes and also in the other material in the Google Drive. I will not derive it over here, but instead I'll just quote how these characters transform, the characters associated with each of the 3 representations transform under a modular S transformation. And so you have 3 characters associated with the 3 conformal multiplets. And under S transformation, namely when we change the argument from tau to -1/tau, we get back these characters, but up to a matrix, that's in the modular S matrix, is a very important object. There's a lot of physics and beautiful mathematics in this matrix. And it hides all the information about the symmetry, as we'll see. It hides not all, but a lot of information about the underlying symmetry of the theory, as we'll see, and takes the following form. Okay, and I will suggest if there's one modular S matrix you want to remember, this is the one you want to keep your mind. Okay, we'll come back to this again, and I think you'll come back. You will see this also again in the last week from Shu Heng's lecture. So this is the modular S matrix for C equal to 1/2. Okay, where H prime. Okay. All right. So now let's analyze the constraints from T and S invariance. Okay. As I said, T and S generate the whole modular group PSL2Z, so it's sufficient to consider these two generators and impose invariance of the corresponding function under these two generators. So firstly, under T invariance. Okay, the condition of T invariance, it says that the spin has to be integral. But as you can see, no difference between this. If the only possibility is to x0 to pair with x0 bar and so on. There's no off-diagonal possibilities. So this tells you immediately that H and H bar, this modular invariant matrix, okay, has to be diagonal. Okay. And the condition from S invariance is something you can easily analyze in Mathematica, if not by hand. And you will find that this modular invariant matrix, okay, it's proportional to the identity matrix. And it's completely fixed to be the identity matrix by the condition that our CFT has unique vacuum. Okay, so that n0, 0 is 1. Okay, thanks for the previous question that closed this logic. And this, together with ansatz, completely determine the Hilbert space of the putative Ising CFT on S1. And we can conclude now that we have three conformal multiplets with respect to both left and right Virasoro algebras in this putative CFT of C equal to 1/2, okay, without actually realizing this CFT by some concrete model, just from the kinematics and general constraints from unitarity and modular invariance, we can already conclude there are only three possible primary operators that are conventionally denoted by identity. So this has H and H bar equal to 0. By epsilon, the so-called energy operator has H and H bar equal to 1/2. And then the spin operator that has H and H bar equal to 1/16. Okay, and the reason they're called energy and spin is related to how this model is realized on a lattice. Okay, the sigma is the continuum model for the individual spins on the lattice, and epsilon is the bilinear in the spin variables, and this is the continuum version of the energy on the lattice. Okay, the two-dimensional Euclidean lattice for the Ising model. That's the first application.
Can I ask?
Yeah.
So the modular variance
Yeah.
comes from putting the CFT on the torus.
Yeah.
This is the Ising data for an Ising model on a plane or
This is about the Hilbert space. It's a property of the Hilbert space. As we said, the most basic thing about the 2D CFT is the Hilbert space, and the only possibility of Hilbert space are Hilbert space on S1. And the point is that after figure out the Hilbert space on S1, you can implement cutting and gluing your general observable and the general Riemann surface down to basic building blocks. The basic building blocks will be the state you sum over at each cutting and gluing circle, together with the OP coefficient that will come in later. Okay, so to completely solve the Ising CFT, we have accomplished half of that. The next step is to fix the OP coefficients. Okay, but what I'm trying to say is that without doing that, the theory is almost essentially fixed already. Okay. All right. The next example will connect to what Nati has talked about in the previous lectures. That is the C2-1 CFT. It's a borderline between the minimum models, which are rational CFTs in particular. They have finite number of conformal multiplets, just like the Ising model, and they're completely solved. Okay, C2-1 is a borderline in the sense that, as I mentioned, it has a conformal manifold, okay, on generic point on the conformal manifold. Conformal manifold just means you have a parameter family of these CFTs with the same center charge, and their scaling dimension change continuously as you change this parameter. And because of that, this CFT is not rational anymore at a generic point on the parameter space, okay, but it's still solvable. It's a borderline in the sense that there could be potentially more interesting irrational CFTs for C bigger than 1. So application 2, okay, I will not have time to go into the detail, but let me just give you a flavor of what is the general space of this seek to 1 CFTs. Okay, note that I say seek to 1 CFT because nowhere have I specified the potential Lagrangian description for this theory. Okay, the Lagrangian description comes out when you try to mimic the spectrum we'll find just from this general argument. Okay, but a priori you don't need the Lagrangian to solve this theory. Okay, that's the merit of this axiomatic approach to DCFT. So in particular, in this case, because C is above, is at the threshold, the unitarity constraint is no longer as strong as before, and consequently, H, the value of possible values, the possible values of the composable weight H that are compatible with unitarity is now there are infinite possibilities. Okay, the only constraint that H has to be bigger or equal to 0. The C-equal 1 CFT has been classified, so I will not run that analysis. But it has been, so even though you have this infinite possibilities, okay, so it sounds like impossible to have infinite possibility for the representations, okay? This is going to be an infinite sum, okay? In particular, you have this momentum winding operators. They are each labeled by an integer. So in particular, in this sum, you will have this double integer sum. So that sounds like a very complicated thing. But you can still run this analysis coming from modular invariance, okay? And it has been classified what are the possible matrix that sits here. Now, infinite dimensional matrix. And those matrices are parameterized by continuous parameters, okay, which is a real number, which I'll denote as R, because this will turn out to be the same R up to a factor of square root 2 that showed up in Nati's lecture when he discusses the compact boson. Okay? And in particular, something interesting happens. First of all, so I have a factor of 2, so this is the point, so it's really a half line, okay? The equivalent modular invariant R parameterized by a half line. It ends at this point square root 2, and this is the so-called, the theory that at this point is realized by the SU2 level 1 WZW model. This model has a further enhanced symmetry than Virasoro symmetry compared to a generic point on this one parameter family, and that enables the truncation of this, okay, this infinite sum in this particular case into a finite sum, where you can package many of the operators here into a multiplet for an enhanced symmetry that's further enhanced that contains Virasoro. Okay, so this has the so-called affine Kaz-Moody symmetry that contains Virasoro with equal to 1. And correspondingly, the primaries, there are again a finite number of primaries with respect to this enhanced symmetry. So even though there are infinite number of primaries with respect to this Virasoro symmetry, because of the enhanced symmetry, you can reorganize your spectrum again, and you find a finite number of primaries. And they are labeled by conformal weights H equal to 0 and 0. That's the vacuum. And just one other primary operator with H and H bar equal to 1/4. Okay? And you'll hear from Nati, hear more about this model and this interesting symmetry structure from Nati tomorrow. That's all I'm going to say about SU2 level 1. This is not the whole story about the SIG1, the family of solution to the modular constraints for this center charge. Okay? As some of you may know, there are another branch, okay, that's take out at R equal to square root 2 times square root 2. Okay? Again, there's a factor of square root 2 compared to Nati's lecture. And this is also a PKT point, which you have heard a lot about. There's a lot of interesting physics when you study how you approach this point from the lattice. But from this continuum description, there's nothing so special, apart from the fact there's additional marginal direction that emerge from this direction. And they'll call this direction R hat. Sorry, R prime. And it turns out it's more in terms of the concrete construction, this can be identified with the radius of the orbifold theory. Okay, so it's better to just call it R orbifold. So explicitly, this branch, this continuous branch, can be realized explicitly in terms of the compact boson with this corresponding Lagrangian that you have already seen from Nati's lecture. And the orbifold case is nothing, but it's literally the same action, okay? But rewritten R with the replace R with R orbifold, and subject to the condition that phi is identified with minus phi. Okay, that implements the charge conjugation orbifold. And in terms of its orbifold radius, R orbifold, this point corresponds to square root 2. In other words, from this description, this point arises from SU2 level 1 engaging a Z2, doing orbifold by Z2. We'll review the general.
It's on the web.
Sorry, we will review the general notion of orbifold and all the interesting physics, in particular relation to symmetries, anomalies, and so on later. Okay, this is not yet the complete story. Okay, so if you do it carefully, what you will find is that in addition, the space homogeneous invariance as equal to 1, in addition to this this branch structure, also has 3 isolated points. Okay, they are commonly referred to as T, O, and I. Okay. The reason being referred to T, O, and I related to this tetrahedron, octahedron, icosahedron. Okay, and these margin variants are explicitly realized by CFTs that coming from gauging discrete symmetries in SU2 level 1. Okay, correspond to the so-called A4, the alternating group of rank 4, and S4, the permutation group, and A5. Okay, so these are gauging a subgroup inside SU4, the global symmetry at this enhanced symmetry point. Okay, the SO3 is a particular subgroup that's anomaly free. Okay, for those of you who know this language, and that allow you to implement the orbifold consistently. Question? Yes. And sorry, so just one point. And you may know that there's an ADE classification of discrete subgroups of SO3. And this corresponds to the E6, E7, E8 type discrete subgroup of SO3. And the other orbifolds, if you try to do the A and D type orbifold, will land on this line if you do A type. Will land on this line if you do D type orbifold. Okay, so we don't miss anything. Question? Yes.
It seems like if you give the discrete symmetry,
Yeah.
then your structure change the whole, so you have to jump feature.
That's right. That's right. Discrete gauging is something that's very mild. This is true not just in general dimension. In particular, it's an invertible process. And center charge, I didn't emphasize, is unlike counting degrees freedom in the Lagrangian, is an extra good, unambiguous count of degrees freedom in the CFT. In particular, it has the feature that under RG flow, it will decrease. Okay, and in particular, so it will be contradictory if the doing discrete orbifold, which is the invertible process, actually changes center charge. Okay. All right. So that's a very quick review of the power of. So I just want to emphasize again, okay? In reaching at this space of possible margin invariance, we did not use that there's a potential Lagrangian description. You can forget about Lagrangian quantum field theory at all, and you will reach this diagram. Okay. But the nice thing is that the miracle is that all the points on this diagram, including the discrete points, are realized by concrete quantum field theory constructions. Okay. And this will continue to be the case in many examples I'll discuss. And this kind of is a hint of the very strong constraints coming from modular invariance. You are not imposing the full set of constraints that a CFT observable needs to satisfy. Okay? But even before that, the theory is already completely fixed. All right, so the third application of modular invariance, which I think is very important, but a little bit tangential to what I'll focus on the next lectures. But otherwise, I think it's important to mention it whenever a modular invariance is brought up, because it's a very powerful universal statement you can make just from modular invariance without focusing on any particular CFT. And this also highlights yet another physical feature of the central charge C as a count of degrees freedom in this quantum field theory. And this is the so-called Cauchy formula. And this will also connect to the lectures given by Juan about black hole physics. Okay? So the Cauchy formula, as we'll explain, is a way to characterize universal behavior in the spectrum of heavy states. Heavy meaning energy of the corresponding state or operator is large compared to the central charge. So something I already emphasized, the central charge C is a count, it's unambiguously count of degrees freedom that's possible when you have a conformal field theory. Okay? This notion generalized to higher dimensions as well. To derive the Cauchy formula, in other words, this asymptotic density of states, we don't need to use the full power. Well, you can derive various refinement of this Cauchy formula by considering more general configuration of the torus. But to derive the most basic but already quite powerful statement, we should just restrict to the case when the torus is rectangular, meaning there's no spatial twist. That is the case when tau is equal to 2 pi I beta, where beta is also known as the inverse temperature. Okay? Or cited differently, the torus Poynting function in that case, in the case when tau is purely imaginary, is nothing but the usual thermal Poynting function, okay, for the two-dimensional CFT. In this case, the Poynting function on the torus is a function of beta, and it will take the same form as over here. Okay, but instead of using this form, I'll write as an integral for the reason that'll become clear soon. In the following way. Okay, so I'll be doing things in a rather crude way because this will already lead to a non-trivial constraint. And as I said, there are various refinements that you can get by doing things more carefully and turning on more parameters. Okay, so what do I mean by here? This is just a different way to rewrite the general torus Poynting function over here. But for the moment, forgetting about the full conformal symmetry, the Virasoro symmetry, just remember the dilatation symmetry. So we can grade the states corresponding. Okay, so this is the weight from given operator of dimension delta, and rho can be thought of as a discrete sum of delta functions that keep track of the spectrum in delta. Okay, and the statement we'll be making is about this density of states when delta is larger than C. Okay, that's the famous Cauchy formula. So how do we do that? We want to use the modular S invariance. So we can look at two limits of this Poynting function, the so-called high temperature and low temperature limit. The low temperature limit corresponds to beta much larger than 1. Okay? As usual, when beta is much in the low temperature limit, the thermal Poynting function will be dominated by the vacuum, by the ground state. And that's obvious from this right-hand side because the exponentially damping. Okay? For beta is very large, it's just dominated by the vacuum, and this is the leading contribution, subject to subleading exponentially suppressed terms in large beta. On the other hand, if we take the high temperature limit that corresponds to infinitesimal small beta, okay, then we'll be in the regime where all the states, high energy states, contribute equally, okay, because this weighting factor goes away. And in the extreme, in the rough approximation, this will be a count of the states in the system. Okay? So if you forget about rigor, this is literally the number of states, okay, in the Hilbert space. okay, by definition. Of course, it's infinite, so that's why I put the quotation mark. Okay? But the way it becomes infinite is correlated with the right-hand side because of the modular invariance. By modular invariance, we know z of beta is equal to z, the Penning function, where beta is sent to 4 pi squared over beta, just from tau to minus 1 over tau. What this tells us is that these two limits, the divergence you see in these two limits, are related. Okay? You have an exponential divergence over here as beta to infinity. You have a divergence over here from summing over all the high energy states. Okay? And you can figure out, just by knowing the fact that these two are related, okay, and using this equation, you can derive the famous Carty formula that says that the density of states when delta is much bigger than c, okay, is approximated by rho 0 of delta, which is equal to this famous formula. So it has to be something that's divergent enough to produce this exponential divergence. It cannot be just divergent, each divergent fast enough. And the answer of this calculation that comes from inverse Lagrange transform, inverse Laplace transform, takes the following form, okay, up to corrections. So there are 1 over delta. So over here, there are 1 over delta corrections and also non-perturbative corrections, exponentially small corrections. I realized this you cannot see. Sorry. Yeah, so if there's something that you cannot see, just shout out. I think when I get to the corners, I have a tendency to cram too much stuff.
Yeah. Is it a Carty formula in higher dimensions? The sentence are, say, 4 dimensions.
Yeah. So there's analogous Carty formula in higher dimension where you study the theory not on torus, but the higher dimension generalization S1 times SD minus 1. In which case, the C will be replaced by the free energy of the theory on the S1 times SD minus 1. Okay, so there's an analogous formula. Yeah. All right. Okay, but that's not. But what the point I'm trying to make is that that F has nothing to do with the conformal center charge. There's no clear relation between that free energy coefficient to the conformal center charge.
Sorry, that's not the A that shows up like in the A theorem, for example?
Sorry?
That's not like the A that shows up in the A.
It's not, yes.
Oh, okay.
Yeah. So that's why that's where the two-dimensional case is more powerful. Yeah. Okay? All right. So here I was just saying that the corrections are either 1 over delta, which usually refers to as perturbative corrections in this limit, or exponentially suppressed. Okay? This is a powerful formula. It's a remarkable formula for the density of states that are purely determined by a single number c. Okay? There are various consequences of this formula. One immediate consequence of this formula is that if you look at the microcanonical entropy in the CFT, okay, which you can think about as a thermal system when you put on this torus, it says that, okay, I don't have space here. So this is a remarkable formula. In particular, this formula for rho, or more precisely, this asymptotic form in this region where the energy of the states, or the scale dimension of states, much larger compared to C, implies microscopic entropy just from taking the log of the density of states. That goes like something is purely fixed by the center charge. Okay, emphasize again here, I'm talking about the density of states that are not necessarily primaries. They're just dilatation eigenstates. You can refine all these formulas by focusing on primaries. That will introduce various shifts in C, C minus 1, and so on, okay? Sorry, yeah, C minus 1 over 24.
Is the delta in the square root or not?
Right?
Is the delta in the square root?
Delta is in the square root, yes. Okay. Well, in any case, you should double check by implementing the Laplace transform, okay? All right, inverse Laplace transform. Okay, so what are consequences of this it's inside the square root. Yeah, what are consequences of this important formula? There are many important consequences. Out of the many, one thing that you probably all know is the famous, it enables this famous calculation in strong major of alpha. Okay. That reproduce the Bekenstein-Hawking formula for 5-dimensional supersymmetric black hole by microstate counting. Reproducing the Bekenstein-Hawking entropy formula. And the way it goes is that there's an effective 2-dimensional CFT, okay, that enters into this microscopic microstate counting problem. And the states in that CFT, okay, known as D1, D5 CFT, are the putative microstates for the black hole at strong coupling. And you can count the spectrum of those you can count the density of states in that CFT using this formula by just knowing the center charge. And then you can translate the parameters in this formula to parameters that parameterize a black hole. And you can see this formula match on the nose with the Bekenstein-Hawking entropy for this supersymmetric 5-dimensional black hole. And more generally, later people realize this is not something special. It's something that holds also in a more general context that explains, that give you a microstate counting for to explain the BTZ black hole entropy. Okay, and this is via ADS CFT, where the microstates, okay, this is in particular ADS3 case, where the microstates that that account for the black hole entropy for the BTZ black hole correspond to higher heavy operators in the 2-dimensional CFT on the boundary. Okay. So this completes this very brief application, but very important application of modular invariance of 2-dimensional CFT. The last application, which is not something I will come to this lecture, but hopefully in the next lecture or the one after the next, is, as we'll see, okay, this modular invariance, this very simple constraint, SNT invariance, okay, when you combine with putting in topological defects that implement symmetry twist without specifying details of the topological defects, will give us a powerful way to discover first features of symmetries, okay, in a very intuitive and quick way, okay. In particular, such features could be associated with anomalies, okay. And as we'll also see, a similar type of argument, namely the modular invariance of a torus binding function dressed with symmetry twist, would allow us to discover new types, generalized symmetries in a given CFT. And in general, these symmetries will be non-invertible, which is a notion which I'll come to if not at the end of the lecture, next lecture. Okay? So this is more like a advertisement for what we'll cover next. Okay? But before getting there, as I mentioned already, the axiomatic framework for 2-dimensional CFT, okay, a priori does not end with just modular invariance. Okay? There are also other constraints that look highly non-trivial. Okay? And they are complementary in a sense. Okay? But in these lectures, I chose this modular invariance as an entry point. Okay? Just to to make it more or less self-contained. Okay? But I feel I should still say a few more words about this general axiomatic constraints. That, for those of you who have heard it before, these are the most general set of bootstrap axioms, okay, for a two-dimensional CFT. Okay, so once again, modular invariance is just one corner of this huge zoo of axiomatic constraints. So as I said, we are focusing on theories that are unitary, local, and has conformal symmetry, and also bosonic and a unique vacuum. Okay, and the locality, okay, implies that we can cut and glue the Padding function that involve arbitrary insertions, okay, and that will lead to the same result, namely the consistency under cutting and gluing. That's the notion of locality I'm using here. And by using that, you can see that the independent set of CFT data to fully specify the theory, okay, which I refer to as CFT data, consists of the scaling dimensions of the states, okay, or the local operators that lives in the Hilbert space on S1, okay, and also the 3-point coefficient Cij, okay, that tells you the 3-point functions of any of the 3 states in the given Hilbert space. Okay, I, j, and k label 3 potential primary operators or primary states in the Hilbert space. Okay, and it's a consequence of conformal symmetry, the Virasoro symmetry, actually, that all the 3-point functions that involve the conformal descendants are determined by just this number. Okay, so for example, the Cijk I wrote in the first lecture that depend on z, that is completely fixed by this single integer, single number. Okay, that does not depend on the coordinates. Okay, and this is also known as the OP coefficient, because it carries the independent information that went into taking OPE of 2 operators and expanding into single primary operators and these descendants. Yes? Question, yes?
This notion of locality
Yeah.
excludes the existence of non-local operators?
We'll come to that, yeah. Yeah, there's a refined version of locality when you have defects, which will be important when we do symmetry twists, yes.
Also, this data,
Yes.
like non-local operators, you would need more data to characterize the CFT?
Yeah. You will come to that, yeah. You're getting ahead, yeah, but that's, yeah. Good. So this is, as I said. Okay. All right, so it turns out it's a non-trivial problem, okay? But it's a non-trivial problem solved by Moore and Seiberg. That to ensure all these conditions, okay, the basic building blocks need to satisfy a set of necessary and sufficient conditions. And these necessary sufficient conditions come in 2 families. 1 and 2, and this is known as sphere 4-point crossing. And this is known as the modular covariance of torus 1-point function. Okay, let me explain what they are. But the key point is that this 2 set of conditions, which are very much restricted, is non-trivially sufficient to ensure this locality property, arbitrary Riemann surface of genus G with n operator insertions. Okay, so this is doing on sphere.
Found this on the web.
Okay, maybe Siri should do the lecture for me. Yeah. So anyway, so what I'm trying to say is that this 2 set of conditions, which you impose just on the sphere, okay, and also on the torus, is sufficient through cutting and gluing, okay, to together with this data to ensure this consistency of this cutting and gluing condition on general Riemann surface. And that's a non-trivial theorem proved in the paper of Moore and Seiberg.
But
Sorry?
What is N?
N is the number of local operator insertions. So I'm being kind of schematic here. You need to also specify the moduli of the Riemann surface and the location of the insertions. Okay. So what are these constraints? The modular constraint perhaps is not so surprising. Okay, it's a modular covariance of the one-point function, and the modular invariance we're talking about is just a special case when the local operator insertion is identity. Okay, but to impose the full set of conditions, you also need to study the modular covariance with a single operator insertion. And I didn't put any coordinate dependence in the insertion. It's because you have translation symmetry on the torus. So this one-point function is just going to be the function of the modulus of the torus, nothing else. So I can freely just suppress the position dependence. So what is this first condition, okay, and how it comes about from cutting and gluing? Okay. The so-called sphere 4-point crossing. And this is what some of you asked previously. This is equivalent to imposing constraints from associativity. Okay, so associativity comes in here. It's coming from locality. So it's useful to compactify your complex plane, the Euclidean spacetime, into a sphere. So this is our spacetime by including infinity. Maybe make it easier to draw pictures. And suppose we have operator insertions 01, 02, 03, 04. Okay? And this is the observable very interesting. So this corresponds to the case of genus 0 and equal to 4, okay, where we have operator insertions which have suppressed their position variables. Now, a general way to calculate this correlation function, so this can be thought about as 4-point function on the plane, is that we can choose a circle to quantize the theory and expand. Okay, so what I want to do is that I can quantize the theory on this circle. Okay, and that allows me to do OP. So once you understand the language, of course you don't need to draw the circle anymore. You just need to do the OP of 01 and 02. Okay, but the proper way to think about it axiomatically is you do quantization along this circle. These two operators inserted in this upper hemisphere create a state on this circle. And you can expand that state into this primary operators at the top. Okay? And that implements this convergent OPE. So doing that, and doing also for the state created in the bottom hemisphere, leads to this kind of diagram that you probably have seen many times if you have been to a bootstrap talk, where schematically this represents you take the OPE of operator 1 and 2, take the OPE of operator 3 and 4, and the OPE is expanded into primary operators and descended labeled by I, and you sum over all these blocks. Okay? But emphasize this picture is schematic in the sense that all these lines, they do not have actual meaning in terms of topological defects because you have seen them in so many drawings. So I'll put a quotation mark just to emphasize this is schematic, okay, to avoid any confusion. Now, instead of locality, is the key of locality is that we are free to choose the circle we want to quantize the theory on. Okay. So in particular, we can choose instead this circle to be our quantization circle. Okay. And we run the same argument. So over here, instead of this kind of decomposition channel for the 4-point function, we have instead this channel where we take the OPE of 1 and 3 and 2 and 4, and then we decompose into a bunch of operators being exchanged, which we label as K, and together with conformal descendants. Okay, again, I put a quotation mark. And these two pictures are clearly related by something that look like crossing, and this is the reason why it's called crossing, because they have to be the same, because we're just calculating the same observable by doing different way, by looking at different way to decompose the same observable. Okay? So this is the famous 4-point crossing equation. And there's a lot of work on this, on deducing constraint on CFT by studying these equations instead of the modular bootstrap equation. And the merit of this kind of equation is that they allow you to probe the OPE coefficients, which are hidden in the modular bootstrap equation that we looked at. Okay? Okay, so they are complementary. And in particular, you can solve, so by analyzing this equation, you can solve Ising CFT completely. Okay, so once you normalize all the operators to have trivial unit 2-point function, okay, the only non-trivial OP coefficient that you find by solving the OP coefficient, non-trivial meaning OP coefficient is non-zero, is the OP coefficient between 2 sigma and 1 epsilon. And by solving this bootstrap equation, you'll find that it's equal to 1/2. Okay, and I'll refer you to some details that's revealed in Xi Ying's TASI lecture note, I believe, from 2017. I think I put this also in the Google Drive folder. And you could ask, which I will not have time to explain, but you can ask me afterwards, whether there's a powerful application of that crossing equation to produce something like a Carty formula, but not for the density of states anymore, but instead for the OP coefficient. Okay, because here, the OP coefficient enters here and here, here and here. Okay, so indeed, there's a Carty-like formula. For OP coefficient that you can deduce by analyzing this crossing equation. And these apply to OP coefficient that involve 2 light operator and 1 heavy operator. Okay, the heavy operator is again being exchanged in the middle, and 1, 2, 3 are taken. 1, 2, 3, 4 are taken to be light. Okay, so that's the 4-point crossing constraint.
It's just 5, so we should
come
to.
Okay. I think I did better, but okay. I think maybe Siri should really take over. All right, so let me just wrap up. You say, do I have 5 minutes or?
No, I was 5 minutes.
Maybe I start late.
This is the bargaining stage.
Okay. All right. So let me wrap up by just explaining what this modular covariance condition is. I think okay. It's modular covariance of which you can picture it in a similar way. So here, instead of looking at sphere, you look at the torus, okay, the boundary of your bagel. You have a local operator insertion here. Let's call it O. Okay. And again, you can use your imagination and figure out which circle you want to choose to quantize the theory. Okay. You are free to make your choices and derive your own bootstrap equation. But the one that's going to be relevant for this statement is going to be the following 2 circles. So I use the red to draw this circle. Okay. I can cut open this torus in this way, okay, along the circle. And instead, I can also cut the torus along this cycle. Okay. So there's 2 different ways of quantizing the theory on this manifold with this operator insertions. Okay, will lead to 2 expressions. One expression is just torus 1-point function, which is nothing but the same trace we had before. Okay, with the q to the L0 minus c over 24, q bar, and so on. But now with the operator insertion. Okay. The other is similar, but with tau inverted, because these 2 cycles are related by S transformation. And after keeping track of this wild transformation that's involved when you do the S duality, when you do this large diffeomorphism that induced S transformation, there's a subtle factor that you need to include that leads to this covariance property rather than the invariance property. And the covariance property says that these 2 are almost equal up to some factors that essentially coming from a conformal transformation. Okay, so this is the subtle factor I'm talking about, which are absent for h and h bar equal to 0, obviously, in this way. Okay, and the small exercise for you is to just from this property to show that the exercise is show that this 1-point function is 0 if the spin of the operator is odd. Okay. Just a small exercise to play with the modular covariance property. Okay, so this is the more cyber conditions, and a priori you may be wondering is you will be imposing this set of condition for all operators in your putative theory. Okay, so you have some putative guess for the spectrum, and you have some guess for OP coefficients, and then they're subject to these conditions, which are kind of polynomial equations. Okay, and there are infinite number of them if you have infinite number of primaries that you want to consider, which is generally the case. Okay, when you go beyond the minimum model, you may wonder whether you will have actually find explicit solutions. And even for the minimum models, because you have such a huge family of equations, it's a priori not clear whether there's a solution. It looks like the system is over-constrained. Okay? But there's a powerful three-dimensional perspective on all these equations, as explained in the paper from Morse-Seiberg, that there's a three-dimensional TQFT, where the structure in the three-dimensional TQFT, together with some defects in 3D QFT, guarantees a solution to this set of equations. Okay? We won't have time to get into that, but next lecture, we'll start talking about discrete symmetries, where we dress this torus with symmetry twist, and we'll use what we said over here. We'll implement what we said over here to discover features of symmetries and also discover new symmetries. Okay? That's the end of this lecture.
Well, we will see you all tomorrow.
Okay. All right.
Can you
Yeah.
give us a flavor of this cutting and gluing? Like, how can I say it?
Can I get the mic?
Oh, yeah, of course, of course.
I just want to make sure it gets
Charged. Yeah, definitely. Yeah, sorry for going over time.
Oh, it's all right. That was a good stopping point, I thought. This is a very, very
Yeah,
nice
yeah,
lecture. I need that too.
Yeah, yeah.
Thank you.